All right, please.
Okay, so thank you very much for inviting me here. Thanks to the organizers. So I have to go out of the nickelates word and go back into the iron-based superconductors. So what I will reconnect also with the previous talk, and suggest that iron-based superconductors are a good platform to explore heavy fermionic physics systematically within d-Electrons compound. So what do I mean by this? So first let me thank my collaborators. So these are some young people that were in my group along the last years, and what I will be showing is something that I've done in collaboration with the Würzburg group, partly with the Trieste group, and the experiments, on the other hand, are done in Karlsruhe in the group of Christoph Meingast. So heavy fermions, I guess that we all know that there's many, here quote something that I liked, cerium copper 6 is an F-electron compound, and just by inserting one atom of cerium in a matrix of copper, you go from a specific heat. This is the Sommerfeld coefficient, so the slope of the specific heat going towards zero temperature, from a small number, 0.6 millijoule per mole Kelvin square, Kelvin square, to 1,600, which is one of the main hallmarks that we look at when we look for heavy electrons. This huge specific heat means huge density of states of the quasi-particles at the Fermi level, very, very heavy masses. And there are 45 years of research on this. There's so many of them that I didn't want to make a list. But they can have this Sommerfeld coefficient even higher than 1,600, and most of them, even the smallest one, are of the order of fractions of 1,000, so like 400, 500. Now, these guys are all done with compound, like you see here. The key player is cerium and F electrons, rare earths or actinides in the compound. Now, there are some heavy fermions known that do not have F electrons. The main one, the most known one, is lithium 102O4, that has a interesting Sommerfeld coefficient of 420 millijoule per mole Kelvin square. Again, I don't know why these two is come down here. But then there is yttrium, manganese 2, zinc 20. There is some doped ruthenate, and these are done, of course, with d-Electrons, so transition metals. Now, what I'm trying to highlight is that these are systematically found with F electrons. These are completely serendipitous findings. And then let me mention, since Aline was here, I think she's not here anymore, that there are also proposals with p electrons, so on graphene, and as we discussed before, magic angle twisted barrel graphene is also seen as a heavy fermion problem, and flat bands in general give a very interesting twist to this story. But when you look at materials and specifically these high values on some of the coefficients, you really realize that F electrons are the key players, and the d electrons could be efficient, but the finding here is completely serendipitous. So now, why don't you like F electrons? Well, you might say, well, it depends. They're completely nice, but if you want to do material engineering, rare earths are not so rare as the name says. That's a misnomer. Cerium is pretty frequent, but they can be problematic to extract, to treat. Some of them are radioactive, and we've heard a lot about them in the news, so you know that these are critical to some extent, even politically. So why not having platforms to do this nice physics without F electrons? And that's what I'm trying to push. A proposal for systematic search and exploration of d-Electron heavy fermions is that doping a Hund metal towards half filling gives you systematically heavy fermions. And of course, some heavy fermionic behavior was being hinted at in the diagram of the iron-based superconductors, and we managed with experimentalists to try to put this paradigm to work, to push this concept, and we extremized this heavy fermionic behavior in the family, one of the families of the iron-based superconductors. So I don't know, it seems to me that almost everyone knows perfectly the physics of iron-based superconductors, so I will go very fast on the overview. There's many families. These many families have only as a common block the iron plane with ligands above and below that can be chalcogenides or pnictides. They have high TCs of the order of 30, 40 to 60 Kelvin, many of them, and they basically, if you do they have tetragonal symmetry or some orthorhombic distortion, and if you do DFT, you get more or less the correct Fermi surface topology, that is a semi-metal compensated with a hole of pockets and electron pockets, and you have mainly the 5 bands coming from iron 3D orbitals at the Fermi level. Split just a little, so all of the orbitals of the iron 3D orbitals are participating. They disperse 4 to 5 electron volts, and they host 6 conduction electrons in these 5 bands. Or, I mean, if you look at them in the one iron picture. Now we all know that this gives a nice scenario for explaining the superconductivity and the magnetic order, but I will not really enter into that. So one of the family I like most is the 1 to 2 family. Most because what I try to highlight is that doping of the carriers in the plane is a super fun knob to play with, and the 1 to 2 family is the one that you can actually dope a lot, from the electron side to the whole doped side, and typically you dope electrons by putting cobalt instead of iron or other transition metals in the plane, and you put holes by putting, as you know, potassium instead of barium, and you can synthesize a lot of compounds, and you can get even to the stoichiometric case in which you have fully replaced barium for potassium, so you have potassium 1 to 2, but you can even further substitute isovalently with rubidium and cesium. And superconductivity does not really go away, but it becomes small. However, what goes away is this magnetic collinear stripes. One key point that I like to highlight is that all the way the normal phase, which is above superconductivity, is tetragonal and it's a Fermi liquid. So you really see everywhere T-square behaviors. However, Fermi liquids, you have effective masses, and they have effective masses do something really interesting. If you look at the Sommerfeld coefficient along the family, it goes up and up and up, these blue points. And if you do DFT, it's basically constant. So this is really the textbook example of a strongly correlated material. When DFT gets so far away from the experiments, clearly interactions are playing a major role. And if you look at the isovalent compounds, it's even worse, because then you substitute potassium for rubidium and cesium, and you get this Sommerfeld coefficient to go even up, and you start entering the ballpark. This is like 150, 180 start going towards where the heavy fermions are. So the key point I'm trying to highlight is that the stoichiometric compound barium 1 to 2 has 6 electrons in 5 orbitals, and by the time you've got to potassium, rubidium, and cesium, you have put alpha hole per iron in the plane. So you're at 5.5 electrons in 5 orbitals. So almost at half filling. Half filling would be 5 electrons in 5 orbitals. Okay. So you have to weigh towards half filling, and you've got these correlations to go up and up and up. Now, what do we do with the theory here? Well, we try to understand what the interactions do, and if we do our DFT plus slave spin or dynamical mean field theory. This basically state spin is an easy way of doing something that resembles to dynamical mean field theory. So if you include the dynamical correlations due to the Coulomb interaction and the Hund's local exchange, you get these green points, which really tell you that this is the physics at play. Here we use only one value of the interaction and then just change the doping. So it's really the doping, which is increasing the correlations more and more. And if I take away the Hund's coupling, this is just to say, this behavior goes back to basically to the value of DFT. So it's really Hund's coupling, which is the key player giving these correlations here. So how do we do this? Well, we take a DFT calculation. We do a tight banding parameterization, so where this Ti, J, and M prime between the 5d orbitals of iron are all estimated by ab initio, and then we add the interaction. This is the simplest form that does the trick. Of course, the interaction has also off-diagonal terms, but we neglect them here. They're only quantitatively important a little bit, but qualitatively all I'm saying can be done with this kind of interaction where you have repulsion of the electrons in the same orbital, parameterized by U, and then a reduced repulsion when the electrons are on the same or on different orbitals on the same site, and even more reduced if they're aligned their spins by being in different orbitals. So this parameter that reduces the interaction is the makes the electrons prefer to be in different orbitals with aligned spins, is the Hund's coupling, is a fraction typically. It can also be estimated ab initio correctly, and it's a fraction of the Coulomb interaction, and that's why we put so that's why we call it Hund's coupling. So because it embodies is what causes the isolated atom to embody the Hund's rules, which are that you construct the atom the way you know, so privileging to align their spins. So it has an extremely important role that we all know in chemistry, in isolated atoms and insulators. This has been studied for decades. I'm not talking about that. What I'm talking is that this Hund's coupling has a strong effect in metals, and I like to make this very simple example. I will be talking for now a little 10 minutes about models which have the same interaction but have simplified bands, and then we will go back to the iron-based superconductor band structure in detail. So, which means basically that here, instead of doing all the complicated Ti, J, and M prime, I can put like nearest neighbor hoppings between the same orbitals. So I will have 5 bands with featureless density of states. Anyway, the key point is the local many-body dynamics. So it's really embodied by the interaction. I can really show you the parallel between the results that we have in these models, like 3-band Hubbard model, 5-band Hubbard model, and the full 5-band DFT plus DMFT calculation in the nictides. The local many-body physics is really the same. So bear with me now when we go through these Hubbard models with featureless bands, and you will see, by the way, that results in the 5-band, 3-band, or 2-band Hubbard model with this Hund's coupling are very, very similar. So if I take a 2-band Hubbard model, for instance, and I only put intra-orbital repulsion. So of course these bands are completely decoupled. It's just a mind experiment to say that there's 2 bands, because these 2 bands don't talk to each other with the hopping, don't talk to each other with the interaction. So it's a stupid thing. What you can increase the interaction strength. And what I'm plotting here, and from the next part of the talk, is the quasi-particle weight, or the inverse mass enhancement. For when the interaction is 0, you have z equal 1. And when the interaction increases, you have a reduction of the quasi-particle weight, which is an increase of the mass, which means reduced metallicity. When this thing hits 0, you have a Mott insulator, okay? Which means that the interactions localize the electrons on an integer number of electrons on each site. Now, this is what I have in this sum of single-band Hubbard models. Now, if I turn on the repulsion between the orbitals, so I have more repulsion. You would expect that I have increased correlations, and maybe I would have a faster mod transition as a function of the interaction strength, and this is wrong. You have a mod transition at larger interaction, which is somewhat counterintuitive. And if you now reduce part of the interaction, so you do what we do with the Hund's coupling, so reduce the interaction in the interorbital case, and even more if you have parallel spins, maybe you say, okay, now I've reduced the interaction, I should have a more weakly correlated model, and you have the opposite. So the mod transition arrives very fast, even faster than in the single band case. So it's counterintuitive, and it really tells you that you cannot.
Yes. This question, is it a mod transition or selective mod transition?
That's mod, because the bands are identical. Yeah, true mod.
I see.
Yeah. I see. And this is simply telling you that you cannot simply view the competition between band delocalization and interaction strength. It's more complicated than that. And the complication is exactly what Hund exploits to make a more correlated compound. So let me get into a little more detail why this is complicated, because what you need to take into account is local fluctuations, so the number of degenerate configurations locally that you have to form quasi-particles. If you have a very symmetric interaction like this one, you can combine a lot of local configurations, and this makes a quasi-particle that has an easy time going around. If you constrain electrons to respect that they have to align their spin when they find themselves on the same site, well, you're making their life difficult to hop around. And that's, so these constrained local configurations that we select increase the correlations, and so increase the mass. Okay, this is one effect. And the other effect, this is just a cartoon. If you have two electrons in two orbitals, you have 6 states which are degenerate if you don't put Hund's coupling, and if you put Hund's coupling, you have a multiplet splitting. And so you reduce the degeneracy, and these configurations are the ones that you have to use when you hop around the lattice, and so you have a constraint that makes your life harder. And this is true also for 3 orbitals.
Yeah, Luca, sorry if I may ask on the previous slide. The feeling, what was the feeling?
Half.
Half feeling.
Yes. So another thing that does the Hund's coupling is changes the distance between the charge sectors, because we are in metals and we have fluctuations. And one thing I like to highlight is that, okay, this is a complicated graph, but it just tells you as a function of the chemical potential where is your ground state with 2 electrons, 3 electrons, 4 electrons, and this is half filling, so it's 5 electrons in 5 bands. And what I'm trying to highlight is that Hund's coupling makes these charge sectors very close, so you can fluctuate easily between all the sectors below half filling, or between all the sectors above half filling, but then makes half filling really dominant, in the sense that there is a long plateau of chemical potentials where the atom wants to be half filled. So half filling is a special case because all the other sectors are brought close, and so the charge fluctuations are easy, but the half-filled sector is brought far away from the others in terms of energy, and this makes it special. So these two effects can collaborate. So the distance between charge, the easiness of the charge fluctuations, and the number of configurations in the ground state that you can combine to make the quasi-particles can collaborate or fight among them, depending on the average filling of the material. And we made a little classification with Antoine Georges and Guilherme Mravlier, and we distinguish the half-filled case, where the two effects collaborate to make the system more correlated, because they reduce the ground state degeneracy and they sense all the charge fluctuations to high energy. And you can forget 1 electron in 3 orbitals or 1 electron in 5 orbitals. When you have just 1 electron or 1 hole, there is no Hund's coupling really doing a lot. But in the cases which are not half-filled and not extremely empty or filled, you have two effects fighting each other. The charge fluctuations are favored, but the splitting of the degeneracy of the ground state makes quasi-particle heavy. So we call this the Janus phase because of some god, Roman god, that has 2 phases looking opposite ways, because these two effects really go fight among each other. So they correlate the system, but they sense the mod transition far away. So they create space for, I mean, space in parameter, in the parameter space, for very correlated phases far away from the mode transition. Now, this is the whole story that got the name Hund metals and then got some resonance. And recently there was a Physics Today by Antoine and Gabi, who sort of made a summary of what we have found in many years. And basically they're characterizing really these Hund's metals as metals where the high spin configurations dominate. So you have to fluctuate to make a metal, but you can only fluctuate through high spin configurations, and this makes your life harder. And this quasi-particle weight has this typical S shape. And here I'm listing a lot of the previous papers where some of these concepts sort of popped up, and we put them together in this nice picture. Gabi, by the way, Gabi Kotliar did calculations for the iron-based superconducting very, very early on, and this was more, of an evidence ab initio, in which he realized that Hund's coupling was really changing the experimental the quantities that you could compare with experiment. For instance, the local magnetic susceptibility or the resistivity were really shooting up when you would crank up Hund's coupling. So that's what brought to the attention to the Hund metallic phase, and he invented the name. What I'm trying to highlight is that that's not all the story, because when you go towards half filling, you go towards a phase which is also Mott insulating, and you enhance this Hundness. So the Mott insulator enhances this Hund metal phase. And these are the quasi-particle weight for a 5-orbital Haber model with 8, 7, 6, and 5 electrons, and you see that this S-shaped behavior gets more and more enhanced the more you go towards half filling. And half filling is really the special case where you get the Mott insulator right away. So if I put that into a nicer graph, this was just to show that the high spin configurations dominate the more you go towards half filling, but I won't enter into this. If you put this in a nicer graph, these are the central filling of a 5-orbital Haber model from 0 to 10. 5 is the half-filled case. This color is the quasi-particle weight. So black is a good metal, and white is a more correlated metal. Here you have the interaction strength for a fixed value of Hund's coupling. And what I put in black bars are the Mott transitions that you get only at integer fillings. So what I'm trying to highlight is that the effect of Hund's coupling is to favor this Mott insulator at half filling and send away these Mott insulators away from half filling. So if I increase now the ratio J over U, you see what happens. So really the phase diagram of this model becomes dominated by the distance from this half-filled Mott insulator. And this square here is where you would put in an equivalent 5-orbital Haber model, the iron-based superconductors. So what I'm trying to argue is that what we see in this phenomenological, by looking at the Sommerfeld coefficient and the correlations in general of the 1 to 2 family, is that the dominant knob is the distance from half filling, where you would have a Mott insulator. So that's the way I interpret, by the way, basically this. Okay? This is, you're approaching the Mott insulator that you would have at half filling, and that's what we're seeing. So with this in mind, I tried to corroborate my picture, and we have actually studied some pnictides at half filling. So this is a little excursus. These are manganese pnictides. So manganese, when you replace manganese with iron, you get directly half filling. And so basically you can synthesize a whole series of changing the pnictide. So this is the 1 to 2 family with phosphorus, arsenic, antimony, and bismuth. And you can find that these are antiferromagnet insulators and have nail temperature exactly in the order of the series here. So from phosphorus down to bismuth, you go from 795, 618, and so on in this order. So we did our calculations just to estimate if these are in an itinerant picture of itinerant magnetism in the sense that these are insulators, but if these are like Slater-like antiferromagnets, or if these are localized local magnetism antiferromagnet, which would corroborate the fact that U is big enough for being in the ballpark where you're beyond the Mott transition for the paramagnetic phase. And that's exactly what we find, because you can calculate the magnetization for all the 4 compounds, which the colors are respected here, and then you can even, I plot here is the difference between the energy of the paramagnetic phase and the energy of the antiferromagnet, which obviously is the ground state. And you really see that you have 2 regimes in each one of these color lines, so for each one of these compounds. A regime beyond this line and below this line, now for instance for phosphorus. And if I look at the differences in kinetic energy and potential energy, you really see that these are weak coupling versus strong coupling. Weak coupling is the Slater antiferromagnet, which is stabilized by the potential energy, which is negative. The difference between paramagnetic and antiferromagnetic potential energy is negative, while the kinetic energy has a positive difference. And then you change completely regime here, and you go on a strong coupling regime, which is stabilized by the kinetic energy gain, typical of a local magnetic antiferromagnetic phase. And this is the same picture that you get for the 4 iron-based, the four manganese pnictides of the series. So let me just flash through them. At different U, you get exactly the same crossover between, the same 2 regimes. All I'm saying is that if we now put the U, the interaction strength with which we model all these systems, and the one that actually was capturing all the correlations of the pnictides realistically, well, you are above this zone. Typically you're here. And in fact, here is where you get the stabilization energy, which can be translated into a TNL, in exactly the same order than realized experimentally. If we were in the weak coupling regime, we would have the inverse order of the Néel temperatures. So for me, yes, this really proves that we are in the strong coupling regime. We are beyond the U of the Mott transition, and in these compounds, typically this confirms again that at half filling you have a localized phase. Then here it turns antiferromagnetic, but that's not the point. The electrons are localized, the firm local moments, and if you dope, you lose the antiferromagnetism, but you have this metallic phase which is dominated by this localized phase, so this Mott phase that you realize at half filling. So for me, this is a nice confirmation of this story. So U is larger than U Mott at half filling. And so let me go through the main point of the talk, since I have this last 5 minutes, which is the following. So I can discuss this with you if you like. There is really a frontier coming from this Mott transition that enters the paramagnetic phase. But the key point is that when you increase these correlations, they also become orbitally selective, as you were mentioning. And this is nicely seen in many experiments. So these black points are the same Sommerfeld coefficient that go up in the family, so I will not mention them again. But if you look at other probes for the mass enhancement, like the optical conductivity, you see a story which is much less impressive. They sort of saturate. And you understand that this is due to the fact that strongly correlated and weakly correlated electrons coexist at the Fermi level in these compounds. So depending which probe you look, you can see a probe which is dominated by the heavy electrons or dominated by the light electrons. So clearly the specific heat is dominated by the heavy electrons. The optics, so the transport, is dominated by the light electrons. And in fact, if you look at ARPES or quantum oscillations that are able to resolve sheet by sheet at the Fermi level, you would see that the estimates of the Fermi velocities, for instance, or direct estimate of the masses which are resolved sheet by sheet, are all concentrated like these red crosses if you're on the electron doped side, and they get spread more and more if you go on the whole doped side. So with the increase of correlations, it increases also the selective nature of these correlations, and you have heavy electrons coexisting with light electrons, which is exactly the situation that we know of in heavy fermions. Also because now, since these orbitals are all hopping into each other, there is hybridization between the light electrons and the heavy electrons. In fact, this is nicely captured by the same theory. So this is the same DFT plus Slade spin. That if you resolve the mass by orbital character, you really see some orbitals increasing slightly and some orbitals with correlations that really shoot up. So we have the d orbitals of iron playing the role of both the conduction electrons and the localized moments that you have in heavy fermions. So within the d shell, some orbital play the role of the original f electrons in the original heavy fermions, and some others keep playing the role of the conduction electrons. And so then comes the experimental part that we have done with the Karlsruhe group. We said, okay, let's take the most correlated 1-2 iron-based superconductor that we have, which is cesium iron 2 arsenic 2, which has an experimental Sommerfeld coefficient of 180 millijoule per mole Kelvin square, and try to dope even more towards self-filling. So how do we do that? We heard yesterday that one possibility is by termination, you have surface doping, but here we tried really chemical doping by substitution in a bulk single crystal, and this was done by putting chromium instead of iron. The reason is that this was already done for barium 1-2. It works. It's very nice because it doesn't change at all or almost the lattice spacing. So it really only introduces holes in the plane and some disorder, obviously, unfortunately. So the group of Karlsruhe was able to synthesize these single crystals in several compositions. So you have here the results, and that's the Sommerfeld coefficient. And for 3% chromium, then there are obviously also solubility issues, but for 3% chromium, they got a record, at least a record for the iron-based family of 270 millijoule per mole Kelvin square. So this is not the highest d-Electron heavy fermion that we know, because we said lithium vanadium 204 had 420, but still tells you that the mechanism that we are trying to push works. You can enhance the heavy fermionic behavior by keep doping towards self-filling. And then, I mean, at some point something else happens, and in fact, for this other composition that they can synthesize, which is 7.5%, you have a complete change of behavior, and the Sommerfeld coefficient goes down. So what actually happens? These are the experimental data. So this is the specific heat data that was in that graph. So clearly you have here the x equals 0, so the stoichiometric cesium iron 2 arsenic 2 with this 180 extrapolation. Then you dope 1%, 2%, 3%, it goes up. And then, of course, at this composition at 7.5%, it goes down again. So something big happens here. If you look at the magnetic susceptibilities, same thing. So, okay, not all the compounds are represented here, but you go from the stoichiometric to the 3% and it shoots up. This is normal behavior of Pauli susceptibility of heavy fermions that we expect. And then something happens all of a sudden for this 7.55%, which look like an antiferromagnetic transition. Okay, this is the typical shape of magnetic susceptibility of an antiferromagnetic compound. And they also, and Karlsruhe, like to look at the thermal expansion coefficient, which is very interesting because it's positive for all these compounds with high Sommerfeld coefficient, and it's all of a sudden becomes negative for this compound with 7.5%. And also the resistivity goes from metallic to semiconducting insulating. So what happens here? Well, this thermal expansion coefficient tells us one thing. There is a thermodynamic Maxwell relation that tells you that if the thermal expansion coefficient is negative, this means that correlations are increased by applying pressure, which is the opposite that we have in the usually. Okay, so the usual behavior in the heavy fermions that we understand is if you apply pressure, you reduce the correlations, and this is the positive thermal expansion. Here you have the opposite, and there is one phase indeed in which this typically happens, is the antiferromagnetic phase or a magnetic phase in general. If you apply pressure, you decrease the effect of interactions, you basically reduce the magnetic moment, and you induce more paramagnetic fluctuations, and this increases the correlation. So this is another confirmation of the fact that we, in this compound, you enter an antiferromagnetic phase that basically kills the heavy fermionic behavior. And we do calculations also of the magnetic phases, and indeed we have always have, as a function of doping, you enter an antiferromagnetic phase. This depends on the details of the parameters, which are not realistic, but so it's always a phase that you find at large interaction and near half filling. So in the end, we obtain a phase diagram which is similar to the famous Doniak phase diagram. So you have increasing masses and increasing correlations going with the knob that we tune, which is doping in this case. And at some point, this phase, this extreme enhancement of the masses is cut off by the appearance of a magnetic phase, so the prevalence of the magnetic correlations. And there's two things I would like to highlight, and this is my last slide. One is why it is important to have this selective correlations is because you might say, okay, even in the single band case, let me approach the Mott insulator, I will have a very high mass. But there you really need fine tuning. Here you have this effect of the heavy electrons wanting to be insulating, so the system might want to do what's called an orbital selective Mott insulator, but it cannot, because it's still hybridized with the light electrons, and the light electrons prevent the heavy electrons from fully localized. And so this is why we get an ample zone of parameters where you have the electrons want to localize, but they cannot. So they become heavier and heavier, and you don't need fine tuning. You just find easily this heavy fermionic behavior. And secondly, that you can show mathematically quite rigorously that local correlations cannot induce an orbitally selective Mott insulator in these multi-orbital cases, because again, the energy to localize just one kind of electrons would be too high. On the other hand, if you include non-local correlations, RKKY or these kind of things, then you can obtain an orbitally selective Mott insulator. So this behavior of extremely heavy electrons never wanting to localize can actually be cut here if non-local correlations prevail, which means that you can find several kind of Doniak phase diagrams which are discussed traditionally in the F electron case. Either some magnetic phase that just cuts the Fermi liquid scale with a first order transition, or a situation in which the Fermi liquid scale goes to zero together with the appearance of magnetism, and you have a quantum critical point happening there. So with this, I will leave you with my conclusions, and thanks for your attention.